Chapter 3 is based on projectiles on a horizontal plane, and later we're going to see projectiles on an inclined plane. The learning outcomes from this chapter are: what is a projectile, how to calculate the position of the projectile at any time, this will be in terms of I and j, velocity at any time, greatest height reached, and the range of a projectile. The four formulas that you might have seen already in chapter 2 if you started with chapter 2. V is equal to u plus at, S is equal to ut plus a half at squared, v squared is equal to u squared plus 2as, and s is equal to the average of the velocities u plus v over 2 times t. V is the final speed or velocity, u is the initial speed or velocity, a is the acceleration, which most of the time we're going to be looking at g, or gravity, minus 9.8 or 9.8 meters per second, or not minus 9.8 meters per second, and t is equal to time. So let's have a look at what a projectile is. So a projectile is any object which is thrown from a point, or fired from a gun, or released from a point on the Earth's surface. It usually flies through the air along this dotted line and lands at a certain point, and what's bringing it back down to Earth is gravity. Now we've two directions here. We've got our y direction and we have our x direction, and there's different things going on in each direction. In the x direction there's no acceleration. In the y direction, g is my acceleration, and the formulas that we're going to apply to these will be based on our four unknowns u, v, a and t, and s as well, displacement. So if we look at the initial velocity in the x direction is equal to u, v of x, we call this the initial, v of x, which my v is my final, and s of x is the displacement in the x direction, the distance between this starting point and this finishing point. So if we apply our formula v is equal to u plus at to this information, with the knowledge that there's no acceleration here, a is equal to 0, we can say that v of x is equal to u of x. And if we apply this information to s is equal to ut plus a half at squared, and still a is equal to 0, we're going to get s of x is equal to u of x times t. So applying this in my y direction to the formulas, we know that the velocity of y, well, gravity is going down, so it's going to be a minus g for my acceleration. So I'm going to change this a to a minus g. So we're going to get the initial velocity of y minus g times t, and my displacement in the y direction, which will help me get the greatest height when we come to that, is going to be s is equal to ut plus a half at squared. I'll write that again. So my displacement in the y direction is the initial velocity of y times t minus gt squared times a half, so I'm just going to write gt squared over 2. So the velocity vector at any moment will be given by v, my velocity vector, is equal to v of x times I plus v of y times j, and my displacement vector, or which is the position vector with reference to the point of projection, is given by the letter or, and that's equal to s of x, the distance travelled in the x direction, times I, plus obviously the displacement of y times j. So let's look at how these relate to questions that could be asked. So we're told a particle projected with initial velocity 14i plus 70j from a point P on a horizontal plane. Calculate the height above the plane after 4 seconds. Okay, so it's something like this. So let's say the height above the plane is here, so we're looking for the displacement in y. And you can see here the initial velocity of y, and we just go back up here going to rewrite this equation that we're going to use when we're asked for height and it's not in terms of. So it's going to be my u of y times t. Now g is 9.8, so g over 2 is 4.9, so it's 4.9 t squared. So my initial velocity of 70, right here, so the displacement of y is equal to 70 t minus 4.9 t squared, 70 coming from here. So t is equal to 4. I get 70 times 4, which is 280, minus 4.9 by 4 squared. And 16 4.9, same as 16 5, take away 1.6, which is 80, take away 1.6, which is 78.4. So 280 minus 78.4 is going to give me 201.6 meters. We'll call them meters. Okay, on to number 2, the horizontal distance from P. So horizontal distance now in this direction. So we're looking at S of x. So displacement of x, you can see up here, my displacement in x, it's just the initial velocity times the time. So S of x is equal to u of x times t, and my u of x is 14. So it's equal to 14 t, 2 seconds, 14 by 2, which is equal to 28 meters. Now, the magnitude and the direction of the velocity of the particle 5 seconds after projection. So for this one, we need v of x and v of y after 5 seconds. So v of x, because of the lack of acceleration in x, v of x is equal to u of x, which is 14, that's 14 from above. And v of y is equal to 70t u plus at. We go back up and just have another look at it. U plus at. So u minus 9.8t. That t shouldn't be there. U plus at, not 70t. So that's t is equal to 5. So therefore we're going to get 70 minus 9.8 by 5, and 9.8 by 5 is 10 5s minus 1, which is 49. So 70 minus 49 is going to be 21. So that velocity vector then is going to be 14. So 14 over here for I or x, and 21 for j. And the magnitude of this from vectors, the magnitude of this velocity vector is the square root of 14 squared plus 21 squared. That, I don't think works out evenly. I'm just going to type that into a calculator. That's going to give me a calculator 25.24, and we're going to call that meters per second. And then the direction will be, well, the inverse tan, the direction, we'll say theta is equal to the inverse tan of my y over my x, or my j over my I, 21 over 14, and we just type that into the calculator to get our direction. It's going to give me 56 degrees, about 0.3, so we'll call it 56.3 degrees, rounded off. Back to the greatest height then. The greatest height. Well, what can we say with this greatest height? It's climbing, it's climbing, it's climbing, it's climbing, and then it's going to start going back down. So you guys know from your general knowledge that at this point we can say it stops momentarily. So the velocity of y at this point will have to be equal to 0 for it to be climbing, stopping, and then coming back down. So let's apply that knowledge. The formula we use for this one, v squared, which is going to be 0, is equal to u squared plus 2as, and it's this displacement we're looking for. So it stops momentarily. The initial velocity was 70 from up here. So v squared, 0, which is v squared, is equal to 70 squared plus twice minus 9.8 for my gravity by s. We could change that s to h if you wanted. So we're going to get 4900, this squared, divided by, if that goes to the left, it's going to become positive. So we're dividing back across by 2 by 9.8, which is 19.6. 4900 divided by 19.6 works out evenly to be 250 meters. So we're going to use this all the time to get greatest height. And then the range of the particle, well, the range of the particle, we can see if I just go along here, starting here, ending up here, that's s of x, the displacement in my x direction. Which we saw was equal to u of x times t. So we need to know the time then. So we have u of x was 14. You can see that from here. So 14t is the displacement in x. So now we just need to go and work out the time, which will always be the case for this range part of the question. So how are we going to calculate this time? So here's my diagram again. So up here, v of y was equal to 0. And you should notice then that down at this point, we can see the displacement in y is equal to 0. It started here and it came back down. So all along here, my displacement for y is equal to 0. So that's how we calculate the time in these questions. So the displacement in y, s is equal to ut plus a half at squared. The initial velocity of y was 70. So we're looking at 70t minus 4.9 t squared being equal to 0. So you're going to factorize this because there's two times. We could divide across by t and solve for just this one, but this is my t is equal to 0, which you'll see now. We factorize this, we're going to get t times 70 minus 4.9 t equals 0. So that's my initial t equals 0 when we factorize and solve. So this one we're going to say 4.9 t is equal to 70. So t is equal to 70 over 4.9. Now that's 100 over 7. And because we have 0.7 in here and we have 100 of them in there, so it's going to be 100 over 7. So t is equal to 100 over 7. And does that work out evenly for us with our s of x 14 by 100 over 7? It does. So s of x, the displacement in x, after 100 over 7 seconds is 14 times 100 over 7, which is equal to, divide there, 2. It's going to be 200 meters. So this is just the intro into projectiles in the horizontal plane. This is the first example. We'll go and look at the second example now before we answer some of the questions from 3A. Okay, so this is the second example. A particle is projected from a point on a horizontal plane. Initial speed 35 meters per second. Angle A to the horizontal, and we're told tan A is 4 over 3. We know from vectors that we're going to need cos A and sin A. So here's my A. Opposite over adjacent, leaving a 5. So cos A is 3 over 5. Sin A is 4 over 5. We have my initial speed. So my vector, initial vector, or initial velocity in terms of I and j, is going to be 35 cos alpha times I plus 35 sine alpha times j, which is equal to 35 by 3 over 5 times I plus 35 times 4 over 5 times j. So that's going to give me 7 3s, 21i, and 7 4s plus 28j. So that's part 1, my initial velocity in terms of I and j. Now we're looking for the displacement vector, or the position vector, at t is equal to 3. And for this, for my displacement and position, I mean s of x and my s of y, or I and j. S of x is equal to u of x times t, no acceleration, and s of y is equal to u of y times t minus 4.9 t squared, applying gravity to this particle. So my u of x is 21t. S of x, 21t, which, what are we, t is equal to 3, which is equal to 21 by 3, which is equal to 63 meters. So for y, my displacement is my 28 times 3 minus 4.9 by 3 squared, and 28 3s is 84, and 9 4.9 is 9 5s is 45, so that's minus 0.9, 44.1. So it looks like it's 39.9 meters. So my position vector, or, is equal to my x, or my I, 63 I, and we have my y, or my j, plus 39.9 in the j direction. In part 3, we've done 2. In part 3, we're asked for the times when its height above the horizontal is 36.4. Okay, we saw in the previous part that time displacement is in y is above the horizontal. So let's say here and here that this is equal to 36.4 meters. So we're looking for the time. So we know we're going up in this direction. So we're looking for the displacement in the y direction when the displacement in the y is equal to 36.4 meters. So my displacement in y is equal to ut plus a half at squared, which you don't have to keep right when you get really good at them, but what was my initial y? It was 28 there, just above, so 28t minus 4.9 t squared. Now I could write equals 36.4 or just minus 36.4 equals 0. Now does this tidy up for me? If I multiply by 10 to get rid of the decimals, I can get 280t minus 49t squared minus 364 equals 0. And I want a positive t squared, obviously 49t squared minus 280t plus 364 equals 0. So it says times, so you should identify from your quadratic knowledge a minus here and a plus here is two minus signs. The first two divide by 7. Does the second one? It does. 52. Let me divide by 7 here. 7t squared minus 40t plus 52 equals 0. 7 is prime, so it has to be 7t times t equals 0. 52. I have a 26 and a 2. Does that with 26 and a 2? I can see it works. 26 2 minus minus. Just double check. I have 26 and I have 14, which is 40. So t is equal to 26 over 7. That doesn't look like a 7. 26 over 7. Or 2. So there are my 2 times. When the height above the plane is 36.4. In example 3, we're told a golf ball is hit with initial speed 12 meters per second in a horizontal direction from the top of a vertical cliff 490 meter high, which overlooks the sea. So here's my cliff 490 meters high. Some golfer decides to stand here and hit a golf ball from this point, and he's going to hit it into the sea, which is not very environmentally friendly, and we're looking for this distance here. So we've got initial speed of 12, with the height of 490, and we can see here this is displacement in the x direction, and displacement in the x direction is equal to the initial velocity times t due to no acceleration. So again, we need to find t. So my initial vector, initial velocity here is 12. It tells us in the horizontal direction, so just in this direction, 12i plus 0j. We can see that s of y, it starts here and it ends here, so just be careful with these. It's going down, so it's minus 490. And s of y is equal to ut plus a half at squared. So the fact that this one is a 0, we just have our gravity divided by 2 times t squared, and that has to be equal to minus 490. So 4.9 t squared is equal to 490. T squared is equal to 490 divided by 4.9 is 100. So t is equal to 10. So it takes 10 seconds for the golf ball to splash into the sea. So s of x is going to be 12 times 10, which is equal to 120 meters. So three nice examples that will bring you into exercise 3A. So practice those before looking at the solutions.